All right, guys, we are jumping to chapter 17 today. We're going to cover a few sections in 17. It's kind of the scramble at the end of the year to get everything in that I want to get in. As a refresher, as a reminder, again, physical changes change the form of a substance, but not its actual identity. Okay, and you can see an example of that right here. It still says the word stampedes, it's just in a different font. But a chemical change actually breaks down the elements or puts them together with new elements and forms a brand new chemically different substance, okay? All chemical reactions are chemical changes. So for this reaction here, my arrow got a little low. Stampedes actually transforms into the word made and steps. The identity is totally different. Okay. So how do we know if a chemical reaction is happening? There's some evidence to look for that will let you know that it's an actual chemical change, chemical reaction, okay? One is a color change. Leaves at the different times of the season, changing colors, that is a chemical reaction. The chlorophyll is changing, there's different reactions going on. That change in color indicates a reaction. Burning, if you burn something, it turns black. That change in color is a chemical reaction. Gas protection, the presence of bubbles, okay? If you mix baking soda and vinegar, the reason it foams up is because it produces carbon dioxide gas, and it makes a lot of bubbles. It makes it very foamy. Same thing with elephant toothpaste, okay? So anytime there is a gas being produced, baking bread, the reason bread is so porous is that baking process produces air bubbles from the baking soda, okay? Changes in temperature. We talked about those exothermic and endothermic reactions. Some absorb heat, some release it. Disposable ice pack, when you put those substances together, it feels very cold because it is absorbing heat. But there are reactions that produce heat. They release heat as well. The elephant toothpaste is one. When it's done, the jar that it's done in is very warm. It produces steam because you can see the steam coming off of the top. The water is being turned into water vapor. This is a weird one. Changes in properties that can't be undone. And really this is baking. You put all the ingredients together, and it's not like you can separate the ingredients out even before something is baked. Like imagine making a cake, okay? It's not like you can pull the eggs out of the batter or anything. But they are still chemically identified as separate ingredients. Once it's been baked, it changes the property, and that is some evidence of reaction. And the last one is known as precipitation. This is not rain. In chemistry, precipitation is the occurrence of a solid forming that wasn't there before. Oftentimes it's from two liquids. You drop one liquid into another, a chemical reaction occurs, and you can see some solids. And it's not like a chunk of something. These are all examples of precipitation, okay? The reaction is occurring, and then you see this like powdery substance kind of float into the liquid. That's precipitation. All right, so let's talk about chemical reactions, okay? Again, they occur when bonds are either formed or they're broken, okay? We talked a little bit about those chemical bonds in our last lecture, okay? Exothermic reactions are reactions that release energy as heat. And for the most part, this isn't 100%, but for the most part, when chemical bonds are broken, they release heat. They're exothermic, okay? Endothermic is a reaction that absorbs heat, and again, not all the time, but in general, those are the ones that the bond is being formed. Chemical reactions require something known as activation energy, okay? And it's just a varying amount of energy that's needed for the reaction to occur, okay? So I have a match here. There are different elements on that match head ready to react, but it's not reacting at all, okay? It needs a little bit of activation energy. And so you strike the match, and that friction gives just enough energy for the chemical reaction to occur, okay? Now it's producing heat. Okay, that's a sign of a chemical reaction, a chemical change. Plus it changed the color of the wood there, okay? It's another example of a chemical reaction, all right? And then finally, just in general, anytime you have a chemical reaction, it's drawn with an arrow there. We probably first saw this when we talked about photosynthesis last year. The reactants, or the raw materials, are what you start with, and then the arrow indicates a reaction occurring, and you wind up with the products, okay? And you can just see a couple of examples up there of different things. Those are both examples of a bond being formed, okay? The rate of these reactions can change, and it depends on different things. First of all, it depends on the concentration of the reactants. If you're using baking soda and vinegar, if I have really watered down vinegar, a very low concentration of vinegar, the reaction's not going to be as fast or as obvious as if I have a higher concentration of vinegar, okay? So you can kind of look at this table right here. What that tells us is that as the concentration goes up, the rate of the reaction also goes up, okay? It's a direct relationship there. Same with pressure. Gas reactions occur much faster under pressure. So the higher the pressure, the higher the rate of the reaction. Same with temperature. The higher the temperature, the higher the rate of the reaction, okay? And you can think of this, decomposition is a chemical reaction. So if you've got leaves or even like a dead animal or something, it's going to decompose faster in the summer because that higher temperature increases the speed of the reaction. If you ever have a glow stick, when you break that glow stick, it glows because there's a chemical reaction occurring. You've mixed some chemicals. If you want to keep your glow stick, stick it in the freezer overnight, and it might actually still last until the next day because that decrease in temperature slows that reaction down, okay? Surface area is another one that changes the rate. If you think of, I don't know, do you guys even know what Alka-Seltzer tablets are? Or like the little tablets you make your Easter egg dye with? If you put the whole tablet into the liquid can only hit the outside surface. So that's how much is reacting. But if you break up that tablet and increase the surface area, now there's that much more reactant available to go through that chemical reaction, okay? So increasing the surface area increases the rate. Catalysts are something that can be added to a reaction to increase the rate, and they basically just lower the activation energy. Our body is filled with enzymes, which are nothing more than a biological catalyst. They help increase the rate of the reactions, and what they do is they give the reaction a place to occur. It's like this little molecule where the other molecules can come in and join together and do their thing, and they leave, and the enzyme's ready for something else to come in. But there's also inhibitors. Inhibitors decrease the rate of a reaction. When dynamite was first discovered, it was so reactive that you could hardly touch it without it blowing up. So they added inhibitors to it to slow that rate of reaction because you don't want things reacting well crazy and willy-nilly like. That is it for our chemical reactions and changes in chemistry. All right, talk to you guys later.